So today we'll go over a few problems from the second problem set, which is again a sort of a review on probability and more of a focus on conditional distributions, conditional PDFs, CDFs, things like that. So there are quite a few problems, but I think I've picked some of them that make the most sense to do. And of course almost all of them which do not have solutions in the back of the book. Some of them which do, which I think are worth going over, but mostly the ones that do not. So let's start with a pretty easy problem. Problem 2.9. Okay. So now we're given the CDF of a probability distribution, and we want to determine its probability mass function. And since we're talking about probability mass functions, the underlying assumption is that the random variable is a discrete random variable as opposed to a continuous one. So let's just write down what the problem gives us. Okay. Okay. So now the first thing to note, and it'll actually be useful in solving this problem to actually draw the CDF, but first of all, let's remind ourselves what the CDF is. It literally means the probability that our random variable is less than or equal to some value b. So in our case, this would be like the sum, say over all I guess here we know that over I less than b, probability I. Let's just draw the CDF, and I think it will become apparent what the probability mass function will be. So. Okay. So we have values 0, 1, 2, 3, 3 over 3.5, and those are basically the important points. So our function takes the value 0 before 0, and then at point 0, it jumps to 1/2. And then it remains 1/2 until up to point 1, where it again jumps to, this time, 3 over 5. And so on and so forth. And you can note that the CDF is a right continuous function. So this means that the right limit always exists, but not the left limit. Or the right, that it's continuous from the right. That's what I meant. Okay, so let's continue on. So we will go to 4 over 5. And then Here we'll jump to 9 over 10. Sorry if it's a little out of scale, but you get the idea though. So now here, we jump here. And finally, at 3 over 5, it becomes 1 and stays there. Okay, so let's see now. What would the probability distribution function be? Where does our random variable have mass? So we note that there's no mass to the left of 0, and suddenly at point 0 we jump up to 1/2. So just by looking at this kind of little ad hoc formula, we can immediately see that at point b equals 0, our random variable has a probability of 1/2. So literally, we can say that if you look at it in this way, this is the probability of 0. And now we keep going. Well, actually, oops, this is wrong. I meant this, P0. So then we keep going and we see that there really is no mass between 0 and 1. But suddenly at point 1, there is another jump. And this time, what does that mean? Well, it means that if you look at it, that this would be the probability of point 1. Because P0 plus P1, which is probability of x being less than or equal to 1, is this value here. So P1 would literally be 3 over 5 minus 1/2, which of course is 1/10. And I think you get the idea, so I'll kind of just go through this a little quickly. These are the other results corresponding to the other jumps. So this would be P of 2, P of 3, and P of 3.5. Okay, and just as a sanity check, we note that all these probabilities do add up to 1. So it's a proper probability probability mass function.
If you were to do that with continuous variables,
Yeah. Well, that is a very good point, because with continuous random variables, there's no such thing as the probability of x being equal to something, right? It's you always only look at the probability of a certain interval. So if you were to do this with in the continuous case, you know, fx is just equal to the integral from minus infinity to x of f y dy. So you can't really do it in the same way, and this really has no meaning. Right? You cannot. It's, you know, you look at intervals. You don't look at specific values.
you multiply that given value equals 0 by a delta function, which you describe. You write a cumulative distribution function in such a fashion so that it would have a step effect like that.
No, that's really. I mean, it's really not the way to look at it. But I mean, I see what you're saying. Like, you want to see the parallel between the two, but they really are pretty different animals. Okay. So, are there any other questions for this? Pretty straightforward. Okay. So. So let's move on to problem 213. Okay. So some of these are pretty easy problems. I'm sure you have no problem doing them. But just for the sake of being thorough. Okay. So an individual claims to have ESP. As a test, a fair coin is flipped 10 times and he's asked to predict in advance the outcome. Individual gets 7 out of 10 correct. What is the probability he would have done at least as well if he had no ESP? So a coin is flipped 10 times, and the hypothesis of him having no ESP means basically that the probability of him guessing right is just one half. There's no positive bias to it. He has no special ability. So if he has no ESP, then X is a binomial with 10 trials and probability 1/2. So, and we want to calculate the probability of him doing at least as well as 7 out of 10. So we literally just want this probability here, because this means at least as well, right? And this kind of answers the follow-up question, which is why do we consider probability of x greater than or equal to 7 as opposed to probability of x equal to 7? Well, it's because it's basically because of the statement at least. So this would just be this probability here. And I guess that this value, oh, we haven't computed it. Okay, so I don't know what this probability is, but you can calculate it. Any questions? Okay. Okay, so now we'll do problem 223, which has an answer in the back of the book, but it's a pretty useful problem just because it shows you what the rationale is behind determining the closed form formula for the negative binomial distribution. So I guess we have a coin. Is it a coin? Yes, we have, okay. So we have a coin where probability of heads is equal to p. And we define the random variable x as meaning the flip, or the flip or number of flips. Say the number of flips required to get R heads. So immediately we kind of note that this is somewhat of a variation on the geometric random variables, right? Where we're interested in the first instance of getting a head or a tail or a success of any kind. This is a little different, it's a little more general, and here we're interested in R heads. In fact, it can be shown that a negative binomial with parameters p and r has the same distribution as the sum of r independent geometric random variables, which kind of makes sense, right? Because each time you want r total heads, but each time you're interested about how much more will I get to get one more head and one more head and one more head and r, and you do that r times. But in any case, So let's see, what would this probability be? Well, we can sort of analyze this as the probability of what has to happen. Well, we have to get heads on the nth try, right? So it's heads on nth try, and then out of the previous n minus 1 tries, we have to have exactly r minus 1 heads. That is the only way that we can have this event happen. So, and then r minus 1 heads in previous n minus 1 tries. Okay? So now, because of independence, we can write this as the product of these two probabilities, right? So if we say that this is event A and this is event B, then this would just be equal to probability of A times probability B, because they're independent trials. Okay? Now, what is the probability of getting a head on the nth try, on the specific nth try? Well, it's pretty simple. It's just P. It's just the probability of getting a head. It doesn't matter on which try it is, right? So this is just P. And now, what is the probability of getting exactly r minus 1 heads in the n minus 1 previous tries? Well, that's just another binomial, right? It would just be n minus 1, choose r minus 1, and okay, we need to have r minus 1 heads, and the rest have to be tails. So 1 minus p times n minus r. And that's how we get the formula. Sure, let me write it. So n minus 1, choose r minus 1, p to the r, and note that when we substitute r equals 1, which is what corresponds to a geometric random variable, we recover the formula for the geometric. So it shows how this is just a direct generalization of that. So are there any questions? Okay. So let's move on then. Okay. So we'll do problem 227, which also has a solution in the back of the book, but I thought it was a pretty good problem to look at. So a fair coin is independently flipped n times. So coin is flipped n times. And out of those, k times by player A, and the rest, n minus k, by player B. And we want to calculate, or want to show, that the probability that A and B flip the same number of heads is equal to the probability that there are a total of k heads. And that is just n choose k a fair coin. So it's 1. Oops. Okay. So let's call this event C. So probability of C it would just be now the sum from I equals, well, I guess overall I, but yeah, let's just say overall I. But of course I can be only the minimum of k or n minus k. So it's the sum over all I of the probability. Let's denote by the number of heads of person A, just A. So that A equals I and B equals I. Okay? Now A and B are of course independent because we can literally view them as person A flips for k times and then person B flips for n minus k times. They're independent trials, so we can break this probability into the product of the two respective probabilities. Okay. Now, what is the distribution of A? Well, it doesn't take much to see that A would just be a binomial, but now with parameters k and 1/2. And similarly, B is a binomial with parameters n minus k and 1/2. So now we can just plug in what we know is the formula for the binomial. So this would be k choose I times 1/2 to the kth power times n minus k choose I and 1/2 to the n minus kth power. Okay. So now we can perform some simplifications here. We note that 1/2 to the kth power times 1/2 to the n minus kth power just becomes 1/2 to the nth power, and that of course can be written outside of the summation. It's just a constant. And then we can also write k choose I, and you'll see why we do this, as k choose k minus I, right? Those two are equal. So k choose k minus I times n minus k choose I. Okay. Now, let's look at this sum a little bit. We basically want to argue that this sum is going to equal n choose k. Now, there are two ways that we could do this. We could either try a brute force type method and just work with the factorials and the combinations here and just directly derive it, and I'm sure that that's possible. But perhaps an easier way and more intuitive way is to argue with a combinatorial argument. So, let's see. So what does each one of these terms really represent? I mean, you could look at it, I know, the way I was always taught combinatorial things, to look at urns and balls and things. So you can look at, say, two urns, urn 1 and urn 2. And urn 1 has, I don't know, has k ball, or let's say n minus k balls. And urn 2 has k balls. And so say that we pick eyeballs from here. In how many ways can we do it? Well, in n minus k, choose I. And say that we pick k minus eyeballs from here. This can happen in this number of ways. Now, if we multiply these two together, then this represents the total number of ways, or the number of ways to pick eyeballs from the first one and k minus eyeballs from urn 2. And now, say that we sum over all I, right? Then we would be summing, you know, the total number of ways to, in total, pick k balls out of both urns. Do you see what I'm saying? So, all right. Close that. Okay. And then, of course, this is just equal to the total number of ways to pick k balls out of n balls, because urn 1 and urn 2 have in total n balls. So this would just be n choose k, which is what we wanted to prove. Is that a little confusing, or is that okay? Any questions? Okay. So we'll move on then. Okay, so this problem is also pretty straightforward. Okay, so we're given the CDF of a function of a random variable. Okay, and we want to, first of all, calculate C in order for this to be a PDF. And then also we want to calculate the probability that x is greater than 2. Okay, so what is the requirement for a function to be a PDF? Well, there are only, I think, two requirements. One of them is that it has to be non-negative everywhere, which will be satisfied provided that C is non-negative. And it also has to integrate to 1 over its support. So let's see, C has to be non-negative. I guess it has to be true, positive for it to have any meaning. And it has to be that C times e to the minus 2x dx has to integrate to 1. Well, we can, of course, we can simplify this because f of x is 0. Actually, let me write f of x here. So f of x is 0 in the negative half line, so we don't take that into account. And we only integrate from 0 to infinity, c times e to the minus 2x dx. And we want to make sure that this is equal to 1. Okay? So let's do a little trick here now. Let's divide by 2 and also multiply by 2. And you'll see why. Okay. Now, can anyone tell me what the value of this integral is? And why? No one? Give you a hint. It's remember the exponential distribution, right? An exponential random variable has with parameter lambda has a PDF that is 0 in the negatives and lambda times e to the minus lambda x in the positives. So of course this is the PDF of an exponential with rate 2. Right? So this will integrate to 1. Because this is a PDF of okay. So what do we get? In the end, we get that C over 2 has to be equal to 1. So C has to be equal to 2. Which is no big surprise, really. We can immediately see that this looks like an exponential. And now, given that it is an exponential, let's answer the second question. So, probability that x is greater than 2, we know for a general exponential it's just e to the minus lambda x, right? So for our exponential, it will just be e to the minus 2, because lambda is equal to 2, times 2, which is e to the minus 4. Any questions? Okay, let's move on. Okay, so 239 is really easy. I don't think we need to do it. As is 247. Let's do 248, which is also very easy. So here, x is uniform, 0, 1. What does that mean? Well, f of x is equal to 1 for x between 0 and 1, and is 0 otherwise. And we want to calculate the expectation of x squared. So this becomes a very easy integral, right? Just be from 0 to 1 of x squared times 1 dx. So, it's very easy. This is just so that you can remember the general formula that if you have a random variable and a function of a random variable, then the expectation of the function is just the integral of the product of the value of the function times the PDF. So this is just a very simple instance of this general formula. Okay. I think I can erase this. This is pretty easy. Okay, so now we'll do problem 3.2, which is a pretty interesting problem. It has a solution in the back of the book, but I thought it was worth doing anyway. And it exemplifies the relation between a geometric random variable and a negative binomial. So let x1 and x2, so x1 and x2 are independent and identically distributed geometric random variables with probability of success p. And we would like to guess the value of probability x1 is equal to I given x1 plus x2 is equal to n. So intuitively, what do you think the answer to this question would be? I mean, we'll go ahead and derive it rigorously, but intuitively, what is this probability saying? Well, it's saying that, okay, say that your second success occurs at time n, then, and also say that the two consecutive successes are independent and they have the same distribution. So the question that we're asking is, well, what is the probability that the first success occurred at time I? Now, just kind of intuitively, since we have the same distribution, do you think that there would be any difference between different i's? Well, let's just say intuitively, a logical hypothesis would be to say, well, any time before time n is equally likely, because the random variables are independent and because they're identical as well. So in other words, everything is sort of symmetric. Like, it could happen in the very beginning, it could happen in the very end. But this is a logical hypothesis to make. So, but let's go ahead and calculate it. Okay. So, well, we can simplify the above a little bit by just saying that this is probability that x1 is equal to I and x2 is equal to n minus I. Okay. Now let's continue here. Now x1 and x2 are independent. So again, we can break the joint probability into the product of the two individual ones. And remember what we argued earlier, that the sum of two independent and identical geometric random variables, or say in more general terms, the sum of r independent and identical geometric random variables would have the same distribution as a negative binomial with parameters r and p. Kind of makes intuitive sense, right? Because you're interested in the first time of getting r successes, which is also the first time that that you'll have r single successes, which is what the geometric random variable counts, and which then we sum them all together and get the first instance when we get the rth success. So this is, let's actually say here, this is probability y is equal to n, where y is negative binomial 2p. So let's see what we get here now. Probability that x1 is equal to I means that I have 1 minus p, I minus 1 times p. And here we get 1 minus p to the n minus I minus 1 times p. And now let's remember the formula for the negative binomial. The n minus 1 over, or choose 2 minus 1 times p squared times 1 minus p to the n minus r. Now we get a ton of cancellations. Did I do something wrong? Minus I, this should be plus 1. Sorry. So everything pretty much cancels out. And we are left with 1 over n minus 1, choose 1. Equal to 1 over n minus 1. Let me just check something. No, sorry guys, I was being stupid. This is of course n minus 1, and this is n minus 2, and things still cancel out. Sorry about that. So any questions? Okay. So we'll move on. So I think, actually no, let's do problem 3.3. Because 3.3, 3.4, and 3.7 are all pretty similar. Okay. So we have random variables x and y, and we have the joint probability mass function. So pxy is the probability that big X is equal to little x, and the probability that big Y is equal to little y. And we're given the following values. Okay, so, and then we're asked to compute some conditional expectations. But before we do that, it'll be useful to just figure out what the probability of x being equal to 1 is, and so on and so forth. 1 and 2 and any other value, and similarly for y. Actually, we only need to do this for y. So let's say that P of x and Q of y are the PMSs. probability PMX. So what is Q of 1? Well, it's just it would be the sum of all the joint probabilities that have a y value of 1 and whatever else for an x value, right? So it would literally be just the sum of this row. And that gives us a value of 2 over 3. And similarly, Q2 is just equal to 3 over 18. And Q3, 6 over 18, 12, it's also 3 plus 5. 6. Sorry. 5, 3. Oh, this is 5. Am I being really stupid? 12, 15. These numbers not right? Oh, yeah. Okay. I see the stupidity. This, of course, is not 2 over 3. Oh, no. Yeah, it's not. It's 2 over 9 plus 1 over 3, which is 5 over 9. This is 3 over 18. And this is okay. Sorry about that. So now we want to compute for I equals 1, 2, and 3. Now remember what this expectation is. This is sum over, say, all j. So probability so this is the definition of this conditional expectation. And we can readily now compute this because this would just be equal to the sum j equals 1 to 3 of j times p j I divided by q I. So we can do this for any single for all those expectations, and we get the following values. Okay. So now just a quick follow-up question, which is actually problem 3-4, but can someone see whether or not the random variables x and y are independent? Well, they're definitely not independent, right? Because, yeah. So it's right here. So and the answer is no. Because we can just look at P11, which we know is equal to 1 over 9. And is P11 equal to P1 times Q1? Remember, that's a requirement for two random variables to be independent. The joint probability density has to be the product of the two individual ones. And this property just fails from the get-go because P of 1 would just be 2 over 9. And we know we've calculated Q of 1, which is 5 over 9. And this is definitely not 1 over 9. So they're not independent. Any questions? Okay. So now let's turn to a few problems that are a little more, just a little different, perhaps a little harder, but in the same spirit. So let's do problem 311. So we're given the joint density of two random variables. When one's positive and x is between minus y plus y, and it's 0 otherwise. Okay, show that, so let's calculate expected value of x given that y equals little y, and show that it's 0. Okay. So the first thing we need to do now is calculate the conditional density, right? So f x y of x given y will be equal to fxy over f of little y. So in order to now find the density of f of y, we need to integrate out x from the joint density. So f of y, we know that is equal to this integral, f of x, y, dx. And we can rewrite this now according to the support, where x can only takes the joint density only takes positive values where x is between minus y and plus y. So we only integrate from minus y to plus y here. E to the minus y dx. And this, after some calculus, gives us a result of y cubed times e to the minus y over 6 factorial. So y, yeah. And we can immediately also kind of just mention here that this is gamma with parameters 4 and 1. Okay. But that's, I mean, it's not really that important. So, what is the conditional density now? Well, it is the joint density. And now here we have to be careful as to where we define it. But it is x squared minus x squared over 8 times e to the minus y divided by y cubed times e to the minus y over, I'm sorry, this is 6, over 6. And this simplifies to 3 over 4 y squared minus x squared over y cubed. And of course, it's only defined for x between minus y and plus y. So now we're ready to calculate this expectation. So, okay. Okay. And this is just now algebra. And this eventually simplifies to 0. Now, yeah. And another reason, and this is mentioned in the solutions as well, another reason why this would integrate, this would have an expectation of 0, is that you notice that this PDF is symmetric about the axis, or about the point 0. And you integrate on a symmetric interval a PDF or a function that is symmetric. So you will inevitably get 0. Again, because whatever you gain on the positive side, you will end up losing with the same probability from the negative side. So sort of intuitively why this would be 0. Any questions? Okay. Okay. Now, problem 312 is very similar, so I'm going to skip that one. So let's do 313. So x is exponential lambda. And we want to find expected value of x given x is greater than 1. Okay. Well, first of all, let's see what is f of x given x is greater than 1. A little x. Then this is just f of x greater than 1, which is lambda times e to the minus lambda x over e to the lambda times e to the minus lambda. Oops, no. E to the minus lambda. And this, of course, is only defined for x is greater than 1. So now to calculate the integral, this would be equal to the integral from 1 to infinity of lambda times e to the minus lambda x over e to the minus lambda times x dx. So this is e to the lambda times this integral. So now we do simple by parts. And we get the following. So e to the lambda times, okay, we integrate this expression and differentiate that. So we get minus x times e to the minus lambda x from 1 to infinity plus 1 to infinity to e to the minus lambda x dx. So we get the following expression, e to the minus lambda plus 1 over lambda times dx. So this, of course, becomes 1 plus e to the lambda times 1 over lambda times probability that x is greater than 1, where x is exponential. So it's 1 plus e to the lambda times 1 over lambda times e to the minus lambda, which is how we get 1 over 1 plus lambda. Okay, any questions? Okay. Oops. So now let's do 337. So, okay. So a manuscript is sent to a typing firm consisting of typists A, B, and C. So let's say X is number of errors in manuscript. Now, if person A types it, then the number of errors let's say Y is the person who types. So if the person who types is person A, then the number of errors will be Poisson with mean 2.6. If, on the other hand, person B types, then the number of errors will be Poisson with mean 3. And finally, if person C types, the number of errors is Poisson 3.4. Okay? And we also assume that each typist is equally likely to do the work. So, and now we need to calculate the expected value of x and the variance of x. So, how do we calculate the expected value of x? Well, we use this very useful formula that the expected value of x is equal to the expected value of x given a certain other random variable. Did you do this in class? Yeah. So, what is now... Okay, so before I do this, what is the expected value of x given y is equal to a? It would be 2.6, right? It would be the expected value of a Poisson random variable with mean 2.6. So it's just 2.6. And x given is equal to 3. Expected value of x given y is equal to c is equal to 3.4. So now this becomes really easy to calculate because this is just 1/3 times 2.6 plus 1/3 times 3 plus 1/3 times 3.4, which just becomes equal to 3. Okay. And just the very similar logic goes into calculating the variance of x. But this time we need to calculate the expected value of x squared. So expected value of x squared is, again, we do the same thing. Okay. Now, what is the expected value of x squared when x is Poisson of some sort? So, let's recall. Right? Which means that expected value of x squared is just the variance of x plus the square of the mean. So for a Poisson random variable, we know that the mean and the variance are equal, right? So expected value of x squared would just be equal to the variance, which is equal to the mean, plus the mean squared. And we do this for every single Poisson random variable. 3 plus 3 squared plus 3.4 plus 3.4 squared. And we get a value of 12.107. Which of course implies then, I'll write it here, that the variance is equal to 3.107. Any questions? No?
Can you explain what that equals to 2.6 squared?
Yes, of course. So this would be equal to 1/3 times expected value of x squared given y is equal to a, plus, the same thing that we kind of did over there. X squared given y equal b, plus expected value of x squared given y equals c. But now each one of these, we know that x is a Poisson, right? So Poisson, x given y equals a is a Poisson 2.6. So the expected value of the square of a Poisson is equal to its variance plus the square of its mean. So this is kind of exactly what we're doing here. This is the variance of x given y equals a, and this is the square of the mean of x given a. And these added together give you the expected value of x squared given y equals a. Okay? Okay, so let's do the final problem. I guess we only need to do part A here. So a prisoner is trapped in a cell containing 3 doors. The first door leads to a tunnel that returns him to his cell after 2 days of travel. The second leads to a tunnel that returns him to his cell after 3 days. and the third door leads immediately to freedom. And now assume that the prisoner selects doors 1, 2, and 3 with certain probabilities. What is the expected number of days until he reaches freedom? Okay. So let x be a random variable denoting the door that's chosen on the first try. And let n be the number of days until freedom. Okay. So let's see. So given that, say that we choose door 3. Okay, there's a little typo on the solution, but it always says door 1. But say that we choose door 3. If we choose door 3, we are immediately let freedom, right? So it will, on average, take us 0 days to become free, because we immediately pick the right door. Let's see what happens, though, when we're not so lucky. Let's suppose that we pick door 1. Well, what is n given x is equal to 1? Well, it means that you're going to travel for 2 days, and then you'll be right back to where you started from. So the total number of days that it will take you will be whatever it would have taken you before, plus 2, because you will have traveled, because you made the wrong choice. So and similarly, if you pick door 2, you get 3 plus expected value of n. Does this make sense to everyone? This is kind of the whole trick of the problem. That if you choose one of the wrong doors, the conditional random variable is basically the same as the unconditional one plus whatever time you will be traveling, because you need to add that to it because you made the wrong choice. So given this information out, calculating the mean is pretty easy. So this is the expected value. We condition on x, and so the probability that we pick door 1 is 0.5. So 2 plus expected value of n. And the probability that we pick door 2 is 0.3. The probability that we pick the right door is 0.2. So we solve for expected value of n, and we get a result of 9.5. Any questions? This is a pretty classic problem with conditional expectation. So if there are no questions, thanks. And see you next week.